And thank you. Thank you for spending the evening tonight together to discuss what happened before the Big Bang and the origin of our universe. I believe that at a basic and very fundamental level is a question and the curiosity and the wonder that we all share as a human species. So I will talk about what we have discovered and seen in science so far, and also a bit of history on how that question has been around for such a long time in philosophy and in the human thinking in general over a few thousand years. So I am supposed to learn technology. Why do we have a question of a origin of the universe? Because we know for certain through our power of observation and technology that our universe did have a beginning. It started 13.8 billion years ago. And therefore it's completely reasonable to ask what was there before. What was there 14 billion years ago or 15 billion years ago? But that question, the word before, implies time. So we get into more fundamental questions about, is time emergent with the universe, or is time fundamental? It's there before the universe existed, and therefore we have the right to ask what was there before our universe existed. Also, our universe has an horizon, which in popular slang is referred to as a edge of the universe. There is no real edge. But that horizon tells us that if we were to move at the speed of light, that point would be the point of no return. We couldn't receive a signal back. And that, again, is a large number, but not inconceivably large. It's 10 to the power 27 centimeters, which is 10 with 27 zeros behind. So we have every right to ask, what's beyond that horizon of the universe? Now, for someone who was born in communist Albania, that was considered the North Korea of Europe, asking questions what lies beyond the border of your country would guarantee guarantee that you'd end up in jail or hard labor or exile or whatnot. So that was a forbidden question. However, there was the sky that we all share, the sky of our universe. And looking up as a child at the sky, I used to wonder, what about kids on the other side of the Adriatic in Italy? Are they looking at the same stars tonight as I am? And are they as curious about the universe as I am, and where did stars come from, and so on. So back to what we know about how stars came to be, and galaxies, and the radiation that was left over from the first moment of the universe's creation, known as cosmic microwave background. It all started with a bang. And of course, what happened before that was inflation. Not economic inflation, cosmic inflation. So a very tiny patch and very smooth patch of space-time had a lot of energy. That's how the story of cosmology goes. And it agrees extremely well with our observations. So that energy stuffed in a tiny patch made that patch blow up and grow very quickly into an accelerated expansion. So the universe grew very large very quickly. As it grows large, it cools down. As it cools down, then all the fluctuations of that primordial inflaton energy, inflationary field, they get converted into photons, which is radiation, and matter, particles. So in the first 3 minutes from cosmic inflation and Big Bang, we go to the first protons and pretty soon into an hydrogen cloud that fills the universe. As the universe continues expanding, not in an accelerated manner anymore, but it's still growing fast, the temperature is dropping down, so matter and light, all these matter particles that were in that primordial soup, in that hot plasma, start separating from each other. And at that point, we have the leftover radiation that we can see separately from the particles in the universe. Under their own gravitational field, wherever you have clumps of these particles, under their own weight, if you like, they collapse. They condense into stars and galaxies and everything that we see in our sky today. And that's the story of our universe in one slide. It's a beautiful story. It starts with only one assumption: a tiny, smooth patch with lots of energy. At the price of that one assumption, you get the whole history for the 13.8 billion years. And everything agrees exquisitely well with all the observations that we have so far, seen so far. Whenever I look further in distance, if I'm receiving some light from a distant star, say 4 billion years away, I'm actually looking at that light being produced 4 billion years ago. So looking further in space, we are looking back in time, and that's how we are able to trace the whole history of the universe up to that moment when light separated from matter. We can see it observationally and see that it agrees exquisitely well with what we understand of the universe. It seems such a natural theory. There is a blast, a bang, inflation makes the universe grow big, and then all these fluctuations produce all the light and the matter that we see in the universe. So why have we got a problem with that? Well, the problem is that it had a beginning. And that beginning is related to something that is a very important law of nature known as the second law of thermodynamics, which says that entropy always grows with time. Entropy is disorder. It is the messiness, is the amount of information that we are missing about a system. For example, in this room, I know how many people and how many seats there are and the color of the seats and the color of the walls, but I have not counted for the fine details of one particle there moving to another side of the room and so on. You can rearrange everything in this room and create more disorder, and still the room would look the same. So entropy is measuring that hidden information about the fine details, about the disorder of the system. As we all know, especially people with teenage children, disorder always grows. And that's the second law of thermodynamics. And that law is extremely important in physics. I'll show you a quote by Sir Arthur Eddington. But it's also the reason why the second law and cosmic inflation, our standard model of cosmology, create an extremely huge problem. And it was this man that pointed that out, that connected the second law of thermodynamics to the question of what gave that energy of inflation and what was there before. So he said, okay, I know what the universe looks like today, Sir Roger Penrose. He said, I know what it looks like today, so I can calculate the entropy of the universe today, and the second law tells me that entropy has grown over time, therefore it must have been extremely small 13 billion years ago, at the first instant of creation. And he calculated that entropy and linked it to the chance, to the probability of our universe coming into existence in this manner. And it turns out that that chance is 1 in 10 to the power 10 to the power 123. Every time I mention a power, keep adding those zeros behind the 10. So that's a zero chance, practically. And that was the huge dilemma since the 70s when Roger pointed that estimate out, the huge dilemma that my community has had. Is there a real problem? How can you have such a beautiful theory that agrees so well with observations like the cosmic inflation and the standard model of cosmology, and yet have it be the most unlikely way to start a universe. It has a nearly zero chance to start a universe. How can you reconcile these two issues? The problem is not very different from the energy prices, come to think of it at the moment. So one way is, well, maybe the second law is wrong, but that law has been tested over and over again experimentally in many different settings. We can't break it. So as Eddington says in that quote, that law holds the supreme position among all the laws of nature. You can't break the second law, otherwise your theory will collapse in the deepest humiliation. Okay, so the second law is not an option. How about cooking different types of beginnings? Why don't we start? We can conceive in our mind any possibility. Why don't we start with a large universe instead of a small universe that goes through inflation? Why don't we have a bouncing universe, one that goes from small to large and back and forth again? All of those models have been tried over the last 30, 40 years, and none of them has worked for this exact same reason, because it does not matter where you start. Yesterday, today, or tomorrow. Going into the future, the second law says entropy will continue to grow. So wherever you started will look very special compared to its own future. And that means that we've got a huge problem in cosmology, and it's the type of problem that required a paradigm shift. But let me mention also the same problem discussed in philosophy, and as I started at the beginning, it's something that we all think, whether we have learned Einstein's equations and quantum theory equations or not. It is something that fascinates all of us as humans. And it's a problem that has been going on for at least 5,000 years in philosophy. The beauty of, at least in my opinion, the beauty of it is that we keep repeating the same group of ideas over and over again. So in philosophy, in Hindu, for example, for philosophy, time is cyclic, and then you have the earth resting on top of an elephant, which is supported on a turtle. As Bertrand Russell mentioned in his pamphlet, Why I'm Not a Christian, you can ask, where is that last turtle resting on? And in his pamphlet, he says, the person he's asking says, suppose we change the subject. So let's not change the subject. Let's keep insisting. And we can look at ancient Greeks. Plato and Aristotle wanted an infinite universe, an eternal universe as well. If the universe has been around forever, then there is nothing to worry about. It doesn't have a beginning. So did Einstein. Einstein put his cosmological constant in his equations by hand, trying to get an infinite and an eternal universe, so that we would not have that problem of a beginning, of a first cause, if you like. But then the atomist thought of the world as made up of atoms. Atoms smash, vaporize, create, and keep creating different worlds and go into smashing process again and recreating again. But they move in, according to Democritus, they move in predetermined courses. I find it fascinating. Epicurus is one of those thinkers from ancient Greece that I find stunning, because he connected a problem which is about nature at the deepest level to free will, to a problem in human nature and psychology. So he said, okay, we are also made of atoms, so if everything is moving in a predetermined course, then we end up being bystanders of our own existence, because everything is predetermined for us, and that can't be. That doesn't sound like fun. So he said, okay, let's allow these atoms to fluctuate, to swerve in their predetermined course. We have many atoms, so the collective effect of those fluctuations is actually allowing for us to make our own decisions, allowing for free will. That is nothing more than 2,000 years later, what became the Heisenberg uncertainty of quantum mechanics, starting from free will, ending up with quantum mechanics. And it's the foundation of the indeterministic nature of quantum mechanics. In fact, even Thomas Jefferson was a great admirer of Epicurus. He wrote that quote, "Here we are today. We are discussing one world, one universe, and some theory that wraps it up, that describes everything, the theory of everything, or maybe many worlds, many things out there behind the horizon of our universe and before our universe existed." That way of thinking did not stop with philosophers. Of course, there was a lot of effort. For example, Husserl, in the 1600s, he spent a lot of time, and he was a very highly educated man. He read through all the holy books, and he figured out that the world must have been created at 6 p.m. on October 22nd of 400 BC. So that dominated. It sounds, I'm having a hard time not smiling now, but that kind of thinking, because of a man of his stature, that dominated for quite some time. Then we had the Aristotelian way of thinking of an infinite and eternal universe, which dominated physics until actually Sir Isaac Newton. For a very long time, Newton gave us a theory of gravity, and then suddenly everything started to make sense about how the world works and how it probably could not be eternal. But it was Einstein that transcended Newtonian way of thinking of space and time as an absolute concept. So Einstein thought of those, although reality is objective, according to Einstein, everything is relative. But both of them, despite their disagreements, both of them agreed that at the very fundamental level, if I have a super microscope and I look at the very fabric of space-time right now, I will see a deterministic universe, meaning that whatever forces are acting on it, I'll have an equation that tells me exactly what is going to happen to that fabric at every moment in time. That would be a deterministic universe, one where we know and we can calculate the future with 100% certainty. At around the same time, we have in Copenhagen and Germany, Max Planck, Niels Bohr, Heisenberg, and Schrödinger, who are setting the foundations of quantum mechanics. And these men really stood tall against the might of classical physics. Max Planck, like Einstein, his protege, absolutely admired Maxwell, and it was Maxwell's work with Faraday, and here we are in Faraday's old lab, that thought of light as an electromagnetic field. And Einstein so much, and together with Planck, so much wanted to have that kind of geometric construction for all the forces in the universe. So although they were admirers of classical physics, where everything is determined with 100% certainty, once they figured out that there were some fundamental problems, it was the black body radiation at that time, the catastrophe from an oven that should have energies at all possible frequencies, and therefore it should blow up. So that problem was not explained at that time. So studying that problem, they decided it does not make sense to use classical physics anymore, but we can think of light, of Maxwell's electromagnetic waves, not just as waves, but also as particles, as photons. So that was the basis of quantum mechanics. But there is a huge problem there. It is very indeterministic. All certainty about the world is gone. Everything has a non-zero chance to happen, from the likely to the less likely. But we can never know for certain what will happen, even if we knew all the forces acting on our system. Now, at small scales, if we are looking at an electron and we say, well, I'm solving quantum equations, Schrödinger's equation, and it tells me that this electron might take this path with 50% chance, or it might decide to take this path with 30% chance. That is fine for the electron. But when you think that the whole universe actually obeys the laws of quantum theory, then it becomes very unsettling. What does it mean to assign probabilities to a universe? What does it mean to have wave functions of the universe where everything is in a superposition? Does it mean that this universe we're looking at is a superposition of many possible universes, each with their own chance to exist? And those are simple questions, but they are also very important questions, and it was the kind of questions that made all the founding fathers of quantum mechanics really uncomfortable. In fact, as I mentioned, Einstein was Max Planck's prodigy. Max Planck did his best to bring Einstein as a lecturer in his university and get him membership to the Prussian Academy of Science. And he wrote that beautiful letter praising what a genius Einstein is. But then there is a footnote there begging the Academy to forgive Einstein's temporary insanity in taking Max Planck's wave-particle duality too seriously to explain the photoelectric effect. So Planck didn't like his prodigy even using his own work to further the cause of quantum mechanics. And that was the reason, because once you start thinking of the implications of quantum theory to the whole universe, then it seems to become a mess. Niels Bohr said, okay, I can solve the problem. I have this wave function of the universe with many branches. Each branch corresponds to a possible. It has a chance to become its own universe. But I can collapse that wave function. So out of all the possible realities that might emerge, that have some chance to emerge from that wave function, I can separate them by looking at that wave function, by observing, by measuring it. The moment I observe something, then I know with 100% certainty that this is what will happen. So you trigger a quantum to classical transition the moment you make a measurement, because from a possible fuzzy world of many possible events happening, the moment you have a measurement, then you know that this happened, the others didn't. Problem is, what if somebody else comes along and makes their own measurement? They'll have a different outcome. So Bohr struggled with these ideas in trying to get a classical deterministic universe out of quantum mechanics, and Heisenberg was very much in tune with that. In fact, in his Chicago lectures, he coined it the collapse of the wave function of the universe. By now, it was around for a long time, but by now it's fallen out of favor for many reasons. First off, the moment you make a measurement on the wave function of the universe, you are promoting whoever is making the measurement into a very special judge profile. Secondly, the person or the apparatus, it doesn't have to be a person, or the object that is making the measurement and reporting the outcome of that measurement is classical. Now think of Schrödinger's cats. If you have a cat inside that can be dead, alive, or half dead, half alive, and you put another cat outside, you can't call the second cat, observing the cat inside the box, call it a classical object and give it a special heightened status, only because it's making the measurement. Both entities are measuring each other and reporting on each other. And that was the huge criticism that Bohr faced from this man. Hugh Everett, I heard the song before from the BBC clip. That's Mark Everett, Hugh Everett's son. He has the band deals. So Hugh Everett was a radical. And debate the price. He had a very tragic end. He was a student in Princeton under John Wheeler, who was a close friend, collaborator of Niels Bohr, and who absolutely, Bohr was Wheeler's hero. So Hugh Everett said, you can't do that. Everything, you can't have double standards where the wave function you are measuring is quantum, but the object doing the measurement is classical. So let's agree that the world obeys one set of rules, either completely classical or completely quantum. So let's agree that the world, everything in the world is quantum, in which case, whoever is being measured or doing the measurement, everything is quantum and entangled with each other. Then you get into that Gwyneth Paltrow movie of parallel worlds where everything is splitting up and splitting up. Every time I have a thought in my head, I'm creating another Laura in a parallel universe because my wave function is splitting up. That actually is having coffee at Starbucks now, but rather than giving a talk. So all those possibilities are happening all the time. And that was Everett's thinking about the world. The reason he was absolutely right in criticizing Bohr's approach that it's double standards. Everything has to obey the same rules in nature. However, he used the principle of ignorance. He couldn't assign probabilities at such a grand scale where everything is quantum. So he said, let everything be. Everything will have an equal chance. All the possible outcomes have an equal chance. That's why you keep getting that splitting of the worlds and all the possible outcomes happening at the same time. My colleague at UNC, the second man on the screen, Bryce DeWitt, was the only person that really took Everett's philosophy at heart and actually published his full thesis some 30 years later because he was chief editor of a physics magazine. In fact, he even he found a better name than Everett. Everett had called his theory the universal wave function of the universe. And Bryce said, no, that's too hard to understand. How about the many worlds of interpretation of quantum mechanics? Now, Wheeler, Everett's advisor, dropped Everett at the end. He said, Bohr doesn't like what you're saying. You don't like what Bohr is saying. Can we condense your thesis from 300 pages to 30 pages? And then you get your PhD and you are out. But although Wheeler really did realize how important what Everett was saying was, and he did agree with Everett in that interpretation, he simply couldn't confront and go against his hero, Niels Bohr. So at the end, he chose the middle ground and didn't take sides, basically. So Everett dropped out of academia and physics. He worked for the Pentagon for a while. He ended up being drunk, disillusioned. When Bryce DeWitt came along, it was too late. He didn't care anymore. That was Everett's story. Okay, so people people paid attention to what happened to Everett. And they said, no good ending up drunk and jobless and dying young. So that was the reason for such a long time. One of the big reasons for such a long time, the idea of many worlds and the multiverse was like a no-go theorem in physics, unless you wanted to head towards the graveyard of physics. Instead, the hope was that we have one universe, And there will be one theory of everything that we will eventually discover that will tell us everything we need to know about this universe. And there was a lot of work being done by that, by some really great minds of the 20th and 21st century. And as Stephen, we are in Stockholm there at the conference banquet, in a conference we organized together in 2015, I think it was. Anyway, so as Stephen, paraphrasing St. Augustine, mentions, there is hell to pay for those that ask the question, what was there before? And then there were a lot of variations in how can you possibly make that happen? We know this universe had a beginning, so how can you get around that issue? Of not asking what was there before the beginning, of not asking of the first cause, what gave that beginning. And there were many, many ways of closing up, either heading to a singularity, which was the Penrose-Hawking theorem, a very famous theorem, or closing off that first initial moment and incising it, and then all you have to worry is what happens later. So there was a lot of research done, but eventually, it led everybody to a multiverse. And by eventually, I mean in this millennium. Another reason why the multiverse was considered as really a bad taste in physics is a very good one. You can't have a scientific theory unless it's falsifiable, unless you can come up with predictions that can be tested. How can you possibly test the existence of a multiverse? I started this talk by saying we can't go outside the horizon of our universe. So I can't go with a camera and take a snapshot of the multiverse beyond the horizon of our universe. And that was one of the key elements that put people off taking the multiverse seriously. However, everything changed. So what happened now? What happened in this millennium? First, there was a discovery in '98, experimental discovery by a supernova group that got the Nobel Prize. They found that 75% of the universe's energy is this mysterious dark energy. Everything else, as the universe grows, the amount of particles you have in there, the density will dilute because you are making the volume bigger. So will light and photons, not this energy, because it's like it keeps a constant density. So the amount you put per unit volume in this room, for example, is a constant. So if I double the size of this room, then I've doubled the amount of energy. It's like nothing we have seen before in science, except at the first moment of creation of the universe, but we weren't there to witness and understand it then. So it's very mysterious. It makes the universe grow into an accelerated expansion, like cosmic inflation did, and we have no idea what it is on the nature of dark energy. We know for certain that it will be the sole element left in our universe pretty soon, when the universe has grown so big that there is barely any matter and photons around. The only thing left will be the dark energy. So energy ruled the beginning of the universe, and dark energy will govern the future, the end of the universe. That was one ingredient, that discovery, that added urgency to understanding what gave that energy of inflation. The other one was string theory. Now, string theory was based on Einstein's dream and all the founding fathers I mentioned before, in unifying all the forces of nature, just like Maxwell had done in his electromagnetic theory, under one umbrella theory of everything that would explain our universe. The price you pay in string theory is you start off with 11 dimensions. In our universe, we have 4: length, height, width, and time. In string theory, you throw in an extra 7. Now, if you can explain the unification of forces and actually, at the end of the day, in whatever manner, reduce those dimensions so you end up with one universe that looks just like ours, that would be fantastic. It's a worth it price to pay. And that's what string theorists tried for so long, for decades. Trying to find ways of curling up, making the extra 7 dimensions really tiny, so that in our daily life we think our universe is 4-dimensional, but if we were to look like extremely close at the fabric of space-time, then we would see that it's stringy in nature. After doing that exercise very successfully, there was an embarrassment of riches. So they did get a universe that looks exactly like ours. And that was great, and all the forces, gravity with the other 3 forces were unified. The problem was that they didn't end up with just one universe. They ended up with a nearly infinite number of such universes. Of course, it went against the goal of having one theory and one universe, but it was suddenly throwing at us, at the physics community, a multiverse, because each one of those, and that finding was coined the landscape of string theory, where each potential value on that landscape is the potential energy for a Big Bang to start. So that made the whole physics, initially it was considered a crisis of physics in general, string theory in particular, but pretty soon people realized that that's what you get, and string theory is still the leading candidate for that underlying theory of nature. So those were the 2 reasons why suddenly the multiverse was becoming fashionable. It was entering the world of physics. This finding of the landscape of string theory happened around 2003, 2004. I mean, the work had been going on for decades, but that's when all the results were put together and it was accepted as a finding of string theory. That was exactly the time when I moved to UNC, and I'm not a string theorist. I'd been thinking at the problem, what was there 14 billion years ago, before our universe emerged, from a cosmology point of view. And at that stage, so that was the lucky part for me, unlucky for string theorists. At that stage, I had convinced myself that the only way to even meaningfully ask that question, why did we start with this one rather than something else, is if you have a pool of possible choices to start from, then that question makes sense. So I was very happy and very prepared for the landscape finding of string theory. And when I read about it, I thought, great, it's derived from string theory. I can just take this landscape of energies and calculate the chance that our universe started from one of those energy values. How do you calculate for the whole universe? That was another big question mark in physics in 2004. So after a lot of walks in very hot and humid weather in Chapel Hill, and beautiful trails, but full of creepy crawlies I had not seen before in my life, I thought, well, it's so simple. The universe is tiny at its infancy, so it's a quantum object. Think of the universe as a wave function of the universe. And therefore, just use quantum mechanics to calculate the chance that we started with this one rather than something else. It was the simplest idea one could think of at that time, but it really worked, because not only did it give me a handle on approaching the landscape and the problem of the question I was asking of the origin of our universe, but it also, for the first time, it provided a way of calculating rather than hypothesizing the answer. So that's what I did. I wrote in a coffee shop. I think by now you know I like coffee. I wrote the words quantum mechanics on the landscape, just in case that I'd forget an hour later, and I didn't. And then I went home and then spent many months doing the calculations, solving Schrödinger type equations for the wave function of the universe on this particular landscape structure, landscape of energies. In this case, the quantum equations are known as quantum cosmology, and actually the equivalent of Schrödinger's equation is the Wheeler-DeWitt equation of John Wheeler and Bryce DeWitt, of the two key people in Hugh Everett's life. That was great. And eventually, of course, I had to also worry, how do you decouple? And I'll show you some more visual pictures in a moment, so you can see what I'm talking about. But you have a wave function of the universe, which, as I mentioned before, it's got many branches. Each one of those branches has a non-zero chance to produce its own universe. And each one of those branches will settle somewhere on that landscape energy. One here, it will take that energy and go through its own bank. One there, go through its own bank. But all of these are quantum entangled into this wave function of the universe. Once they bang and grow, they become classical. So I need to separate them, to decouple them. We can't have that superposition of universes in one. And that's done through something that is called decoherence in physics, that triggers that decoupling of all these branches. But exactly that entanglement that worried me so much in terms of breaking it, washing it out, it was exactly also what later on, a year later, I realized provided the key to testing the multiverse. And then the whole work and the field took off, because it was the first time that somehow, we had a handle on finding evidence and calculating and predicting and testing this, the possible existence of other structures in the cosmos, of not being alone in nature. And the way this works is, as I said, you have this wave function of the universe, and each branch will settle in different points on this landscape of energies and go through growth, just like our universe did. As they are going through growth, they are also decohering, separating from each other, washing out their entanglement. But that cosmic microwave background, that leftover radiation from the creation moment, is being created exactly right at that moment as well. As the universe is going from a quantum wave to a classical growing universe, we're also having the leftover radiation. So that trace of the quantum entanglement is imprinted, is dented, is a fingerprint on our own sky. And that's the calculation we did with and the idea of finding evidence, and the calculation we did with Tomo Takahashi and Rich Holman. We called it the avatars of the landscape. Pictorially, that's I was told there is a red button here for the laser. Yes, there is. So here was one of those branches of the wave function that settled on this energy valley. So the background is the landscape of string theory, which is just an energy landscape. As the wave function is trying to travel through here, different branches will settle in different energies. Each one of those will create its own universe, and they grow independently of one another. But once, at their infancy, when they were just waves, they were entangled to one another. That leftover radiation, which we observe today, this is the present day in our universe. But that leftover radiation, that structure, was created in that first moment when we were still entangled. So whatever the crosstalk between these universes did to our sky, that scar will be visible today. Very weak, but visible. It will simply be rescaled today. These are my favorite illustrations of the theory from Focus magazine in Italy. They wrote an article about this. So here we go again. The yellow background is the energy field, the landscape of energies. And we have the wave function, all the different branches trying to go through. They are still waves here, that's why they are tiny. Eventually, some of them will grow, some others won't. And I'll go through that in a second. The ones that grow will continue to grow indefinitely and look like our universe, but that crosstalk marked here in black, that entanglement between the two, in this case is many of them, that scar will simply be rescaled into the far future. So whatever that little scar is here, it will still be in our universe. Information is not lost. And that's what we calculated. Now, from the moment of the Big Bang onwards, of course, we have the standard model of cosmology, so we know exactly how things evolve. And calculating that quantum entanglement from the infancy days and then fast-forwarding it through the whole cosmological history of our universe allowed us to make predictions on what that signature would look like today. And we made a series of predictions. The most exciting one, the most talked about, is the cold spot. So we said that crosstalk, the black area that I mentioned in that illustration before, that crosstalk is almost like scooping out a part of our sky, scooping out the structure out of our sky. And we estimated that in the avatars paper, we said it's about 10 degrees in the sky. That's huge. All the red and the blue dots that you see in temperature maps of the sky, in the CMB sky, they are less than 1 degree, all the uniform distribution of matter and voids between matter. This giant void is 10 degrees. So that right there breaks uniformity that is expected of cosmic inflation. There were a series of other predictions that the overall strength of those fluctuations that I mentioned at the beginning that produce structure in the universe and CMB. That number is known as sigma 8. It's just the strength, the overall amplitude of those fluctuations. We said that should be suppressed by about 20-25%, and indeed that was also seen by Planck and 5 other predictions. Now, some of those predictions, as for example the temperature fluctuations at the largest scales being suppressed, all of them have been seen, but some of them will never know whether they are a statistical fluke or a real finding. The reason is something known as cosmic variance. Anything that's smaller, you can chop the sky in many samples and then increase your statistics because you can make many measurements. If you are talking for dipole and quadrupole measurements, which is distances comparable to the size of the universe, we only have one universe in which we can measure. So the statistics there becomes terrible, and that's known as cosmic variance. And that's something we can't get around. Okay. So, it seems that we are being guided into that frame of mind where to understand our origin, we really need to allow ourselves to broaden our horizon to a multiverse framework. And in my opinion, that's just a natural extension of the Copernican principle to the whole universe. Not long ago, we thought the Earth is it. We are at the center of the world. Now we know that even our own universe is just a humble member in some corner in that vast but very beautiful cosmos. It's really not a long time in terms of 5,000 years or so. Through the history of ideas about the world, I mentioned Hindus, I mentioned many of the Greek philosophers, and what is our way of thinking now, which really does go very closely, well, it started being close to Plato and Aristotle when we were thinking of a theory of everything, but now even the founding fathers, Hawking was working, trying to come up with a multiverse model in the last few years. Roger Penrose has got a very interesting sequential multiverse model. So all the founding fathers of that theory of everything describing one universe have had that same courage that the founders of quantum mechanics did in shifting direction to a multiverse. But 5,000 years is not really a long time. It's just the blink of the eye, and it's only through curiosity and courage and imagination that, and of course observations, that we have gone that far. And yet, from where I sit, that little, because the further we see, the more we understand how little we know about the beauty and the vastness of the cosmos, of nature. So, of course, many dreadful things can happen in the future, like some doomsday people will tell you, which is true, the sun will burn out, life will be wiped out, true. We might collide with Andromeda, true, but at least we'll know in a few years from it's very likely that we will know in a few years from James Webb telescope whether we are alone in the universe. So we'll know whether our species is far-flung in all the corners and making discoveries and trying to ask the same questions and understand the same universe that we all share and call home. Are we done? Absolutely not. That's just scratching the surface of our universe. We don't still have an agreement on time, the nature of time, being fundamental or emergent. We don't know in what realm the laws of nature exist. We don't know anything about the realm in which mathematics and its relation to the laws of nature. And there are sometimes even my immediate family, when they ask me, are you simply pushing the question of the origin of the universe just one level higher to the multiverse? And the answer is no, you're not pushing, because the multiverse by definition is all there is, all the universes and the structures you can conceive in the cosmos. But not, of course, not the laws of nature, not the mathematics. I'm showing that picture because I want to come back to where I started this talk, and I promise it's the last slide. That is the nuclear reactor in Stockholm. And when we went to Stockholm, of course, all the Stockholm University and the Royal Institute of Technology, KTH, the chancellor is there next to Hawking, they were absolutely delighted. Stephen's doctor, lung doctor, was absolutely furious with us that we went there, because Stephen flew there and he was not allowed to fly. But the Swedes were so happy and really appreciative, and they couldn't please us enough. So they thought they'd do something very special and organized that dinner in the nuclear reactor in Stockholm. It's right on campus of it's right on campus of KTH. It used to be a nuclear reactor, not anymore. But so they thought, okay, these people have gone to restaurants, they've seen Stockholm, we'll do something that only we can organize. Take them there. That nuclear reactor, there was a special decree of the parliament after Chernobyl where that is not a functioning reactor anymore. But that nuclear reactor is probably related to the reason I'm here today talking with you about these beautiful questions. When Chernobyl blew up, people were going to work in the nuclear reactor at KTH, and their badges were beeping like crazy. And it was early morning, so the first thought they had was, there is a leak on that particular reactor. And they check everything, there is no leak. Then they go outside and everybody's badge is beeping. Then they start measuring around town, and there is a lot of radiation around town. So by 8 o'clock in the morning, they figure out that radiation is not coming from Sweden, although they decided to shut that reactor, but it's coming from Chernobyl. So they called the US and all the NATO countries and warned them this is happening. And later on, Russia also told people that there was this blast from Chernobyl. That event was the first trigger of the Berlin Wall coming down. Because by then it was very clear that the Soviet Union could not continue safely anymore and could not support such expensive enterprises. And it was what triggered Reagan to have that famous statement with Gorbachev, bring down that wall. And Berlin Wall happened about less than a year after that. After Chernobyl? When? Yeah, so it was the same year as Berlin. Yeah. Yeah, so the same year. Okay, so it was very, very closely related. When Berlin Wall happened, although Albania was not part of the Soviet bloc, but of course that was an earthquake, the ripples of which were felt in Albania. And in 1991, there were hunger strikes led by students, which put a lot of pressure on the communist government, and then people took to the streets and brought the statue of the dictator down, and then there was a regime change in Albania in 91, and everything opened up. The US and the UK embassy reopened their doors after nearly 50 years. So there were opportunities again, and borders opened up. Thank you.